is we have a helium atom, a 2-electron system. The electrons are also interacting. We don't have an exact solution, and we are ignoring any kind of spin-spin interactions also. Now, one thing we ask is, what is the ground state energy? If we ignore the potential, it's two independent systems, we know the solutions. We take it as the zeroth order approximation. If you do all the computations, etc., what you obtain for the energy of the ground state energy is minus 108 electron volts. The exact value is around 80, so this is somewhat large. But then we look at the first correction to the energy. That is nothing but the expectation value of the potential for this wave function. Well, it contains a complicated integral, but if you remember there's such an identity, and then you can just go up and look up how it tells you how to separate the different angular components from each other. Then you calculate it, and you get the energy, which is minus 74. Much better. At least the exact energy was 79, minus 79. So it's much better and a much better approximation. But still, we can do a bit better.
Why didn't we take the variational approach?
That is what we will do now. Now, what the variational approach does is it says that, okay, just make up a wave function. And you can just choose whatever one you like. If you make up any wave function, let me identify it with a bar, and calculate the Hamiltonian expectation value of the Hamiltonian for that made-up function, this is always greater than or equal to the energy of the ground state. This is always valid, whatever Hamiltonian you have, whatever made-up wave function you have. And ideally, your wave function will have many parameters in it, and by just changing your parameters, you try to minimize the left-hand side, and you know that your ground state energy is smaller than that one. You put an upper bound on your ground state energy. And if you have your wave function is large enough, it has the number of parameters of your wave function is large enough, and your wave function also is similar to the actual ground state in some sense. In that case, the upper bound will be very close to the ground state energy itself. So here, one approach we can take is, remember the exact wave function was this one. This is the exact wave function we took. Now, typically, if you just imagine the electrons, both electrons are orbiting around the nucleus. For each electron, the other electron will screen somehow the electric charge of the nucleus. So each electron will not actually see the full 2 charge plus 2 charge, but it should see something less effectively. Just imagine if there were a third electron somewhat far away from the helium is neutral, you would say that, okay, there is no interaction, because the nuclear charge is completely screened by the electrons orbiting the nuclei. But since you are looking at an electron sufficiently close, the other electron, which is a single electron, will do a partial screening. So instead of this one, you can choose such a trial wave function. Here, Z effective will be determined by minimizing this matrix element. So what you would do is d cubed R1, d cubed R2, psi bar R1, R2, star minus p1 squared over 2m plus p1 over squared over 2m plus p2 squared over 2m minus z z e squared over r1 minus z e squared over r2 plus e squared over r12 psi bar r1 r2. Okay, this is what you should calculate.
I just missed the point why we are trying to minimize that.
Because of this one. You see, if the left-hand side has some arbitrary parameters, if you change that arbitrary parameter, the value of the left-hand side will change, but still the ground state energy will be less than the minimum value of psi of the left-hand side. So now, the left-hand side will be a function of z effective because my wave functions are functions of z effective. Whatever you choose for z effective, this matrix element will still be larger than Eg, the ground state energy.
The ground state energy
For this helium atom.
for this level.
Yeah.
And this is a experimental result?
No, this is theoretical. You see, theoretically, whatever h, whatever psi bar you take, psi bar h psi bar will always be larger than or equal to Eg. You see, basically, the proof is also not that complicated. You see, psi bar, whatever that is, it will be a sum of exact eigenstates. So, psi bar h psi bar will be psi bar sum over n a n e n psi n, which will be sum over n a n e n psi bar psi n, but this is a n star. Now, ENs are always greater than or equal to EG. So this sum over n a n squared En, if you replace all these coefficients with things smaller, the sum will get smaller. So this is larger than a n squared Eg, larger than or equal to, let's say. Eg is independent of n, but sum over a n squares is just 1. This is just Eg. You see, this is for whatever system you can imagine, whatever wave function you can imagine.
Well, I feel like we already tried to calculate EG.
Yes, that is what we are trying to calculate. That is what we don't know. But I know the Hamiltonian. I can just come up with any wave function you like.
So we already don't know the right-hand side.
We don't know the right-hand side, but I can calculate the left-hand side. And if my left-hand side has some parameters, I can minimize the left-hand side with respect to those parameters, but the left-hand side will still be larger than Eg. And typically, if you have large enough number of parameters, the minimum will be very close, turns out to be very close to Eg.
So why not choose an easier trial wave function? That one looks hard, the integral looks hard.
Well, because of two things. I have a physical interpretation for this wave function. Second, what do you propose as an easier integral? Believe me, this is easy. This is an easy guess. Now, you can say that, okay, this is already a difficult problem. Now, if you try to go ahead and calculate the expectation values of P1 squared over 2m for these wave functions, you are making the problem even more complicated. So this is what I will do. I won't do it, I will leave it as an exercise, but to make it shorter, this is my Hamiltonian. Let me write it in this form. Now z is not equal to z effective, so I have to add the missing terms. Now these four terms, I already know how they act on my wave function. Let me call that H 0 effective. This will in fact give me 2 times that effective squared times minus 13.7. 9 and 7. I already know how it acts. The only thing left is to calculate the expectation value of 1 over R1, 1 over R2, and 1 over R12. Still, it will be a long computation, so I will not do it. But the result looks simple. Yes, this is the result. So I have psi bar H, psi bar. H is the full Hamiltonian, including the 1 over R12 term, and Z instead of Z effective. Psi bar depends on Z effective. So this is equal to Z effective squared minus twice Z effective plus 5 over 8 Z effective times E squared over A0. Now, whatever you choose for Z effective, this is always larger than the ground state energy. Well, how do you minimize this with respect to Z effective? You just take the derivative. So twice Z effective minus twice Z plus 5 over 8. This should be 0. And remember, in our case, Z is equal to 2. So twice Z effective is equal to 4 minus 5 over 8. Which is 27. So Z effective is 27 over 16. Which is 1.6875. So effectively, each of the electrons doesn't see the full two charge in the nucleus. The other electron partially screens that charge by half a charge of the electron, or around half a charge, well, 1/3. It will effectively see a smaller charge. What is the minimum value of this one? Minus 77.5 electron volts. You see, by using this variational wave function, we are much closer to the exact value.
But if you didn't have a good insight on what the wave function would look like, it would be pain in the neck.
Well, you see, you can, for example,
to introduce more parameters, more.
You see, here, we just have a single parameter to change. We can just introduce, I don't know, if you like, hundreds of parameters. And of course, in that case, you won't be doing this by hand. You will be just asking a computer to do all those integrations, calculations of the matrix elements, etc. So that is, in this very simple model, well, it's although it will be tedious, still analytically doable. If you don't know anything, just remember ground states are always, your wave functions always have this shape. Ground states, they look like Gaussians. They will be exponentially damped. They don't have any nodes. You see, ground states don't have any nodes, any points where they become zero except then at infinity. Because if a function becomes zero at certain points, that means it's changing fast, the corresponding kinetic energy term will be large. So that's not something you would like to have in your ground state at least. So you can here we just had an exponential damping. If you like, you could have just chosen a Gaussian with the mean, you would probably put it still at origin. The spread will be one of your parameters. But then the integrals won't be analytically evaluatable. You can just go ahead and multiply this wave function. Multiply this wave function by a polynomial of R1 and R2 with various coefficients. Well, then you will get better answers, but depending on how you should just do a computation. You should only do the computation that you need to do, let me put it that way. For example, would you like to be more precise than 1 electron volt or not in your computation?
No.
Now, most of these computations were done during the first time we knew about Schrödinger equation. But at least, so this much computation already tells me that Schrödinger equation is on the right track. And we even know how to improve this result, if necessary. Now, this was, of course, for the ground state. For the ground state, since the space part was symmetric, the spin part has to be anti-symmetric, and hence this is a total spin. The electrons have a total spin 0 in this case. Now, let's look at when one of them is in the ground state, one of them is in the excited state. In that case, our wave function can be written as 1 over square root of 2 psi 1, 0, 0, R1 psi NLM R2 plus or minus psi 1, 0, 0, R2 psi NLM R1 plus for the symmetric one minus for the anti-symmetric one plus for the symmetric space wave function. But if the symmetric space wave function is the spin should be anti-symmetric, which is S is equal to 0, minus for anti-symmetric space wave function. So the spin wave function has to be symmetric, so the spin has to be 1. Now, what will be the energy? Well, the energy is psi h psi. This will be E1 plus E2. Let me put 0, 0 plus delta, where delta will be psi E squared over R1, 2 psi. Now, what will this be? Let me write it in this form, I plus minus j. This is the notation in your book. I will be V psi R1 psi 1, 0, 0 R1 squared psi NLM R2 squared. It's the diagonal terms. You see, I don't write two terms because these two terms, if you take the square, I can just convert the integral from one of them to the integral from the other one by just renaming R1 and R2. So both of those terms, the square of this one and the square of this one, integrated over all R1 and R2, they will give the same contribution. In fact, when I sum them up, there will be a 1 over 2 from here. It will cancel that 1 over 2. So that is why I is just no 1 over 2 or no factors of 2. This is I, which is larger than 0. J, on the other hand, will be d cubed R1, d cubed R2, again V, psi 1, 0, 0, R1 star, psi 1, 0, 0, R2, psi NLM star R2, R1, well, this is 1, 0, 0. This is again the off-diagonal term. You just multiply the first term from the bra with the second term in the ket, or vice versa. These are called the exchange terms.
The last one is still NLM.
Yes, you are right. And both of these factors turned out to be positive. So what does this sign tells us? Okay, so on one hand we have the S is equal to 0. This is antisymmetric, which tells me that for the space wave function, I have to take the symmetric space wave function, which tells me that I have to pick up the plus sign here, or the plus sign from here. For S is equal to 1, the spin wave function is symmetric, which tells me that I have to use a space wave function that is antisymmetric. That means I have to use the minus sign. But if I take the minus sign, since J is positive, it gives me a lower energy. If I choose the plus sign, it gives me a higher energy, which tells me that S is equal to 0 has a higher energy than S is equal to 1 has a lower energy. Again, I would like to underline, there's no spin interaction in this problem. In the Hamiltonian, there's no spin whatsoever. But still, the energy values turns out to be dependent on spin because of the statistics. So what happens here is, if you have let's say a triplet state, if you have any state, let's say, they basically split into two. The singlet gets higher, the triplet gets lower. So if you look at the helium, there's not just a single type of helium, there are two types of helium. Two types based on the total spin of the electrons. You have either the singlet, either the total electron spin is 0 or 1. If the total electron spin is 0, it has a higher energy than if the total electron spin is 1. And the naming, usually what you expect is your system will be at the lower energy state. So if you look at a helium atom, you would expect it to be in the triplet state. So that's the normal. That is the orthohelium. If you see it in an higher energy state, that is something you wouldn't expect. That is something abnormal, in a sense, in quotes. So that is why it's called para helium. Well, para you usually use for things that are out of the ordinary. Now, of course, for the ground state, this is for one electron is in the 1, 0, 0 state, the other one is in the NLM state. If both are in the 1, 0, 0 state, then the only option is the singlet, and you have the parahelium. because the space wave function is symmetric, and hence the spin wave function has to be anti-symmetric. So it has to be a singlet in spin. Now, why does the singlet state has a higher energy? Okay, this is, let's say, from computation. But why? What's going on? Why do we have this energy difference? Well, it's basically because of this wave functions. Remember the probability distributions? If you have a symmetric wave function, the particles tend to get together. They have a larger probability of being closer together. But if they are closer together, there's an electrostatic repulsion between those two electrons, so the electrostatic repulsive energy gets larger. And hence, the symmetric space wave function has a higher energy. In the case of the anti-symmetric one, the wave function is smaller in the region between the wave function is smaller if their separation is smaller. So effectively, the separation between the electrons in the anti-symmetric case is larger, and hence electrostatic repulsive energy is smaller. So you get in the triplet case, or in the anti-symmetric wave function case, which is the triplet one, the electrostatic repulsive energy is smaller. That's why you get this splitting between the singlet state and the triplet states.
Can this be applied to when both are in NLM? Can this method be applied to two electrons that are in the excited state? Is what I'm asking.
Sure. I mean, you see, the crucial thing in all this derivation is that are the two electrons in the same NLM states or not? You see, nothing in this derivation. The only thing we used in this derivation is that if the two electrons have the same NLM quantum numbers, then their spin has to be different. So their spin has to be singlet. If the two electrons are in different NLM states, then I have this case. I can have symmetric wave function, anti-symmetric wave function, etc. Of course, when you calculate the shifts in these energies or the energy eigenvalues, etc., you have to use the corresponding wave function, but the arguments will still hold.
Can you explain one more time why do we have when spin is antisymmetric, the space wave function gets symmetric and vice versa?
Well, you see, this is the total wave function, which has the space part and the spin part. Under the exchange, the total wave function has to be minus, because they are electrons, they are fermions. The total wave function has to be antisymmetric.
I tried, because also there is the angular parts and there was a connection with the angles.
Okay, so let me continue along this line first. Now, the spin can be symmetric or antisymmetric. This is singlet. This is triplet. Okay. So the spin can be a singlet if the total spin, the spin will be antisymmetric if the total spin is 0. It is symmetric if the total spin is 1. But still, the total wave function has to be antisymmetric. The only way to have this is if the spin is a singlet, the space has to be symmetric. If the spin is triplet, the space has to be antisymmetric. You are right, in general, the space part can be symmetric or antisymmetric. But if you know the spin, let's say that if the total spin of the electrons, you measure it to be 0, then you are sure that if you measure the angular momentum of the state, the angular momentum will be an even number, 0, 2, 4. It won't be 1. It cannot have angular momentum 1. Similarly, if you measure the spin to be a 1, then the angular momentum has to be odd. It can be a 1, 3, 5, but it cannot be 0, it cannot be 2. So that the space wave function will be either symmetric or antisymmetric. Other questions?
So
It's a bit of a detour, but
Hmm?
it's a bit. The book has a throwaway sentence. It says, you said this is one of the early signs that the wave mechanics works. And they say that you can't get this kind of number by the purely algebraic operator method.
Okay.
Okay. What operator method? This is not a
Matrix. Well, you see, if you for the harmonic harmonic oscillator,
right.
yeah, you write A plus A minus, but for the hydrogen atom, it doesn't work. You cannot define the raising and lowering operators.
okay, so it's not like that you get a bad number, you just can't do it. It's-
No, I mean,
Yeah.
if you come up with a method to use this using purely operator methods, that's great. But we don't have such a
Oh,
method.
okay. I was misunderstanding. Okay.
I get that for coupled systems this works like this, right? But for a single electron, the wave function should still be anti-symmetric,
No.
right? For a single electron.
No.
Really?
Why should it be?
Because it's a family. It's still, there is no other particle to take its place.
The
So that's
symmetry,
why-
you see, the symmetry and anti-symmetry we are talking about is under the exchange of two identical particles, not under parity.
Yeah, I was thinking about the parity, I guess.
So what is this restrictions on a single fermions wave function?
Nothing.
So it can be odd, even, nothing matters.
What do you mean odd even? Under parity, you mean?
Yeah,
Yeah, it can be odd or even.
totally different.
You see, that's why you have all these N, L, M values for the hydrogen atom. Depending on the L value, it is odd or even under parity. There is no restriction there.
Right.
Well, let me just make a few more remarks about multi-particle states. More than two. Now, of course, then you can define Pij. This is the exchange ith particle with jth particle. So, for example, if you have, I don't know, a three-particle state, I can have k prime, k double prime, k triple prime. If I act on this with p12, I will get k double prime, k prime, k triple prime. If I act on the same state with p13, etc. So this is just a kind of an obvious generalization. Now, one thing is still this Pij's, if you act them twice the same one, you just have two electrons, exchange them, you exchange them once more, you get this initial state. This still one. So states can be against, they still, each one of them still commute with the Hamiltonian if they are identical particles. You see, if they are not identical particles, then it doesn't commute with the Hamiltonian. But Pij and pKl is non-zero in general. Of course, if Ij and Kl, they are completely different pairs of numbers, just exchanging two pairs over here and two pairs over here, they don't affect each other, so they commute. If Pij and Kl, if they are the same, well, the operator commutes with itself. But if, for example, the difficult terms are these ones. If you have three particles, exchanging these two and then these two is different than exchanging these two and then these two. So they don't commute. Well, what this basically tells me that I have states which are not eigenstates of all of them. I can have states which are eigenstates of all the exchange operators. I can have completely symmetric states or completely anti-symmetric states. I might have them. But I will also end up having states that are neither completely symmetric nor completely anti-symmetric. Now, let's look at one term. We have this K prime. Let me have these two particles are in the same state. Now, in this case, I can't have a completely symmetric state. This is completely symmetric.
İki tane K prime olması ne demek? Yani
Well, K prime, you can think of them as momentum. Let's say that I have two particles having the same momentum and the third particle that has a different momentum. Or if you would like to, I don't know, like treat them as the harmonic oscillators. I have three particles in the same harmonic oscillator potential trap. Let's say two of them are in the first excited state, the third one is in the second excited state, for example. That's what I mean over here. Now, since two of them are in the same or have the same state, then I don't have a completely symmetric wave function. Well, if I would like to write a completely anti-symmetric wave function, then all of them have to be different. So this will be K prime, K double prime, K triple prime, plus K prime, no, minus. Plus K double prime, no, minus K prime, K triple prime, etc. Normalization will be 1 over square root of 6, because I will have 6 independent, six separate terms, 3 factorial. Then I can have mixed symmetry terms, let's say it's symmetric under the first two particles, but has no symmetry with respect to the exchange with the third particle. Well, okay, you can just write down all the rest. Now, if you want to write down the total wave function, let's say, remember, this should still be symmetric or anti-symmetric. Symmetric for bosons, anti-symmetric for fermions. Now, for example, in the expansion of this wave function, let's say that they are bosons, or all three are fermions, let's say. In the expansion, I can have this term, this space wave function, completely anti-symmetric, multiply with spin wave function that is completely anti-symmetric. No. The thing is, I cannot, since these have only 2 spin states, and if these are electrons, the spin wave function cannot be completely anti-symmetric, because since they can be only in 2 states, 2 of them have to be in the same state. And since the spin wave function cannot be completely anti-symmetric, the space wave function can also not be completely anti-symmetric. So what happens here is, for example, you have this state, which is symmetric under the exchange of first two. You multiply it with a spin wave function that is anti-symmetric under the exchange of first two. So you have symmetric, anti-symmetric. If you multiply, you get something that is anti-symmetric under the exchange of first two. Then you have a symmetric wave function in space and the anti-symmetric wave function in spin. You multiply them again, you get a wave function that is anti-symmetric under the exchange of first two. Now you have to write down all wave functions that are anti-symmetric under the exchange of first two, take their linear superposition, and then you have to determine the coefficients in these superpositions so that your wave function will also be anti-symmetric under the exchange of 1 and 3. You see, this wave function is neither symmetric nor anti-symmetric under the exchange of 1 and 3. But the combination, well, let me write it down. This will be, for example, psi symmetric under 1, 2, chi anti-symmetric under 1, 2 with some coefficient, plus psi symmetric, anti-symmetric under 1, 2, and symmetric under 1, 2 with some coefficient b. Neither the first term nor the second term is neither symmetric nor anti-symmetric under the exchange of 1 and 3, for example. But you can choose the coefficients a and b so that they will be anti-symmetric also under the exchange of 1 and 3. And then, of course, already in 3 particles, I'm just being too lazy to write them down. If you have more than 3 particles, well, things start to get more complicated. Now, one thing to write down completely anti-symmetric wave functions is so-called the Slater determinant. So let me mention that one also. For example, if you want to write k prime, k double prime, k triple prime, completely anti-symmetric combination, this will be 1 over square root of 3 this determinant. Well, when evaluating this determinant, just imagine you multiply these 3. Now this is 1 over square 6. K prime, k double prime, k triple prime. Then multiply these 3. Then multiply these 3. Then subtract these 3. And subtract these 3. And then subtract these 3. And you have to be consistent in the order of your products. Well, if you have more than 3 states, 4 states, well, you get a 4x4 matrix determinant, etc. Now, solving the corresponding Schrödinger equation will be more tedious. Let's just imagine if you want to study some large molecule, you have kind of like hundreds of electrons. If you want to look at, let's say, a solid state object like this, you have an Avogadro number of electrons. You have to symmetrize, anti-symmetrize, and do all these kind of tricks, which is not feasible. So we need other methods to solve such problems. Now, one of them is density functional theory, which I will discuss next week.
We won't skip this then, right?
Hmm?
So we're not skipping DFT.
No. I'm assuming you are not all going to be particle physicists. Not all of you. The majority, yes, but not all.
We'll do second quantization this time.
Hmm?
Will we do second
No,
conversation?
that I will skip.
Want to skip this and do second conversation instead?
I mean, we are already most of the example we are looking at is already from the perspective of a particle physicist. So I would like to put some example more related to condensed matter physics.
Two more questions. Will we do relativistic? We'll still do the derivation
Yes.
stuff. And problem solving.
Next week we will have a problem solving. Next week I intend to do this DFT. Probably we won't have enough time to study the relativistic stuff. The following week we will start the relativistic stuff. I will have some additional lectures during the final week. Other questions?
And we cover all of the stuff in the book about DFT.
No.
Can you tell us what we're going to skip?
Hmm?
Can you tell us what we're going to skip?
You should study all of them still. I will just spend 2 hours on DFT, not more. Okay, so see you next week.